I'm personally very interested in building intelligent machines. I've always been. And I think neuroscience, computational neuroscience are very, very important. It's the study of the only instantiation of truly intelligent machines that we know of. All right? There may be other ways of achieving intelligence, but this is the one we have. And so studying it, discovering things about it is critical. But at the same time, reverse engineering the brain, I think, happens to be the longest path towards achieving sort of breakthrough in our ability to build intelligent machines and strong AI and so forth. So while I think it's important, it should be there. I think being biologically inspired, biologically informed is great, but I would also like to argue that it doesn't prevent us from coming up with architectures or overarching architectures with organizing principles that say, wait, this is how we think an intelligent system can be built. Not necessarily human level or even human-like intelligence, but one that we think we can go. And I do agree with the comment of you learn a lot by building. So, personally, I would like to hear, it's great to hear the community sort of evolving and maturing in many ways, lots of interesting stuff going on. I would personally like to see more people aspire, more dreamers, wanting to build thinking machines, or at least be on the path to that. And so, we each have our own approach. I'm particularly a proponent of what's called now emerging as deep reinforcement learning, the idea of merging deep and reinforcement learning, deep learning for scalable perception, reinforcement learning for decision making under uncertainty. And the merger between the two, I think, is an approach, a promising approach for building truly intelligent machines that interact in the real world and solve some of the critical questions or problems like experience-based exploration, exploitation, large state and action spaces, mitigating catastrophic forgetting. People talked about that and so forth. And hardware and all that plays a key role, which is a segue to what Jeremy and I are going to be talking about. You need custom hardware, I think, to scale, mostly because even the off-the-shelf FPGAs as well as GPUs, and I've had the experience in both. I mean, they're great, but they're not uniquely designed, I think, for what we're trying to do, and in particular in the context of memory management. And I think custom hardware is going to play a key role. And DARPA Upside is a program that's somewhat about that. It's got a focus and a charge to try and look at analog computation using existing cutting-edge devices as well as emerging ones, kind of futuristic in a sense, to build, in this case, a workable, sort of state-of-the-art target tracking application. And again, the goal is to build this and demonstrate orders of magnitude lower power consumption, which I think is critical for AI as well, beyond sort of the focus here. And this is what we're focusing on. Some of the key challenges there is analog computation is got all these advantages in power and area and so forth, but it also introduces a lot of distortions and imperfections, noise, additive, multiplicative, some mismatches, nonlinearity effects, a bunch of things that deviate a lot from the algorithm that you have running in C or MATLAB and you really want to implement, in our case, target tracking. And so a lot of the cool research, or cool in my perspective, has been kind of the interaction between the team that models the analog behavior and the algorithmic people, and the back and forth of how can we tolerate this, can we change this, how do we change the algorithm so that it would actually lend itself better to analog implementation. And that has been and continues to be part of the focus of this program. The other thing is, while we want to shift to building systems that are mostly analog to gain the power advantage there, there's still some there's still digital components there, and the interaction between analog and digital remains sort of a key challenge. How do you balance those in the correct way? So just to give you an idea of what we're dealing with, like I said, the application is you have a fairly large visual field with multiple objects. In this case, you got vehicles from an aerial view. And then that information, is streams of frames, goes into the flow here that you're seeing through some back-end pre-processing into a Coors object detection layer into a deep layer, which is the fine-grained, the rich features that are being studied and then mapped through a classifier into hypotheses that goes finally into a target tracking module. And again, the overarching goal here is to implement all or most of this in analog, and thus demonstrating 99% of the compute is being done in analog, and you get 2 to 3 to even potentially 4 orders of magnitude lower power, which is critical for what DoD has in mind. But also, I think it's got a lot of civilian and just other applications if you could reduce. But I think, just as a general comment, I think analog computation is part of the wave of the future because of some of the things, because of the wall we've been hitting, I would say, in the last few years with Moore's Law, and also because they're problem domains like DSP and machine learning that don't need 32-bit accuracy. They could tolerate a lot of inaccuracies and noise and so forth. If your problem is in that domain, and, one would argue the brain is far from being anything close to 32-bit accurate, even 7 bits and nonlinearly partitioned and so forth. If you can tolerate that, then analog computations, even using existing technology, can offer, like I said, 2 to 3 orders of magnitude, lower power, denser, better, faster, cheaper, and so forth. So give you a little bit of kind of under the hood. What we're looking at is, as I said, these images are being fed into the preprocessing. The first preprocessing layer is a Coors detection layer. In this case, we're trying to identify cars. You see various images on the top, the original videos. On the bottom is the sort of heat map of the lower level detection. And as you can see, for a good example is the center image here. Yes, it detects sort of, it's got heat around the cars, but it also has heat around things that are not cars, trees and roads and so forth. But it still reduces the search space so that later when we apply the deep learning layer, we could very accurately say this is a tree, not a car, and that is a car. So it's kind of a pre-processing search reduction layer that is being performed in analog like all the other components. Probably don't need to talk much about the advantages of deep learning to this community, but just going through it in 30 seconds. Deep learning, in my view anyway, is there to deal with constructing meaningful features, mainly driven by regularities in the observations that pertain to high-dimensional inputs. If it's low-dimensional enough, it's not a challenge. But if it's high-dimensional enough, here it's fingerprints, but it could be cars or anything like that. You want a system that captures these salient attributes, salient features of a car, and then you feed that to your favorite classifier, and you usually get good results if the features are good. And traditionally, this has been done manually. A lot of handcrafting of these features, and of course, that's not how the brain works. That's not how we want systems to work down the road. So that's sort of been the selling point for deep learning. And as Jeff and others mentioned, the deep learning has enjoyed lots of success recently in various benchmarks. It's not domain specific. It's autonomous. If it's done right, it learns by itself and so forth. So deep learning is what's common, really, in my view, to all deep learning technologies. And now, now it's emerged. It's a growing field. There's a huge amount of deep learning work out there. But I think what's common is the employment or exploiting the idea of a hierarchy of abstraction, right? You've got a hierarchical architecture where information usually feeds at the bottom of the hierarchy, and as information propagates, more abstract notions are formed. So as you ascend the hierarchy, you sort of gain scope and you lose detail, which is arguably what the brain does to deal with the infinite amount of information we're exposed to every second of the day. But that's really where the commonality ends. Like, everybody's got their own little deep learning variant, and there's mainstreams, convolutional neural nets, deep belief nets. I would argue some of Numenta's ideas do fall generally under that category. But in that sense, for the past 5 years, we've been developing our own deep learning architecture called Destin that we're using in this project. Destin is, much like HTM, is a network of networks. It's a network. The hierarchy comprises multiple instantiations of a basic cortical circuit, a node. These are different colors, but they're functionally identical. They do the same thing. And a node is in charge, has a myopic view of the data, and is in charge of capturing spatial and temporal regularities in these data. And I emphasize the spatial and temporal because it's a big selling point to what we do, and I think it's critical just for AI in general. So again, information comes from the bottom. Each one of these nodes has sort of a myopic, sort of partial view of the data, extracts meaningful information, and then propagates that to the next layer, and that sort of happens layer by layer in a deep learning fashion. And if you extract information not just from the top layer, but from multiple layers there in the right way to, again, your favorite supervised classifier, then you can actually get pretty good results. In this particular application, in this project, we're targeting a linear classifier because it's the simplest one to implement, and it actually does fairly well. In fact, the deviation from a linear classifier to the SVN or neural net happens to be, in this case, marginal. Again, mostly because we think the features that are being formed across the layers are good, are rich, and are discriminative. So yeah, this is kind of unclear here. Just a few words about what's under the hood in each of these Destin modules. What the driving force there is a combination of an online clustering process that is the classic unsupervised learning, tries to capture, sort of anchors around the dense areas of observations, but the twist we've had on that when this was first conceived is, clustering is just spatial information, but we have a feedback loop that, much like recurrent neural nets, if those of you that are familiar with Elman classic recurrent neural net, there's a feedback loop that augments the input space. It takes the external input, augments it with a feedback signal, and the clustering actually takes place over that. So what the clusters represent are not templates in spatial domain, but actually sequences of patterns. And of course, this is happening across each layer. So as again, you send the hierarchy more abstract, sequences that span larger scales are being captured, and this is a small example of a 3-layer hierarchy that uses these basic building blocks, these destined inference modules. We've applied this to all the conventional standard benchmarks more for ourselves, just to see that this is competitive, and you get state-of-the-art results. And in particular, what we've been focusing on in this project and other cases is processing naturally temporal information that has movies or otherwise spatial temporal dependencies that you want to capture across different time scales, and have done fairly well on that. And so with that, I'm going to turn over to Jeremy, who's going to tell you a lot about, or more about, the implementation of all this technology in analog circuitry. Yep, sorry.
All right, thanks, Itmar. So, as Itmar mentioned, we have the destined deep learning hierarchy structure, which is built as a hierarchy. The one that we've built that I'm going to describe today is a 3-layer hierarchy. It's fairly small, but it's 4 layers, 4 nodes on the bottom, 2 in the middle, then 1 at the top. Each of these nodes essentially performs a clustering algorithm, which most of you guys probably know about, but just in case. The idea is to infer some structure about the groupings of the data, and we do that by initializing 4 centroids more or less arbitrarily. We present data, choose which one of the centroids is closest to the observation, update that to move towards the input, and then as we repeat that process over and over again, the centroids gradually, in a data-driven, unsupervised way, move towards the center of the masses of that data. So the clustering circuit that we've built here is it's a 4-centroid, 8-input dimensional clustering circuit. It's organized as an array of 4 by 8 or 32 of these analog computational cells, as well as some circuitry on the periphery to select the nearest centroid to the input, update it, and convert the distances into probabilities to form the belief states that the deep machine learning algorithm uses, as well as sample and hold circuitry to facilitate pipelining between the layers of the hierarchy. So this unit right here is sort of the core. It's essentially our atomic unit. It's the analog arithmetic cell. It essentially is a one-dimensional conditional mean learner, and so we're applying it here towards clustering, where it's conditioned on being selected as part of the centroid that's closest to the input. But it's not too hard to imagine how the same fundamental cell could be used for other learning tasks like classification, regression, and so forth. So diving down into that cell, it's built out of, we have 2 floating gate memories, 1 each for the mean and the variance of that single dimension of the centroid that we're part of. We also have an absolute value operator as well as an x squared over y computational cell. And between those, we can calculate the distance, the Euclidean or Mahalanobis distance between our centroid and the observation. We can also calculate the updates needed to refine our estimate of the mean and the variance of the centroid. And all those different computations can be performed through switching the currents in this cell. Which leads me to the point that we are implementing all of this using analog current mode arithmetic, which gives us a couple of advantages. One is that since we have currents as our values, we can perform summation just by joining the wires together. So we have practically free addition. It also lets us map operations easily using translinear principle into the device physics of weakly inverted transistors. So going down into this, the absolute value and x squared over y circuit, the circuit shown here is the absolute value circuit. So this amplifier here detects the polarity of the incoming current. It's either coming in or going out, and selectively routes that current either directly through to the output or through a current mirror to flip its polarity, turn a sink into a source, and so that performs an absolute value operation. That amplifier also maintains a virtual ground at the input to speed things up and improve accuracy. Then that rectified current goes into a translinear circuit which computes x squared over y. That takes advantage of the, as I mentioned before, the translinear principle of weakly inverted transistors, wherein these two, if you look at M1 and M2, the gate to source voltages are stacked up, so we have two voltages, and because weak inversion transistors have an exponential voltage to current relationship, the stack up of those two voltages corresponds to a squaring in the current domain. Then that the variance current goes into the Y input, to, which corresponds to dividing that, and so the output is the absolute difference squared divided by the variance, which is a single element of the Mahalanobis distance. And so when we test it, we can see that we sweep the input and we get this parabola corresponding to the distance, which as we vary the mean and the variance, we can shift or broaden or narrow that parabola, as you would expect. So then that's the Z output coming out of here is a single element of the distance between the input and the centroid. That goes out, it's wire summed, and goes into the next stage, which is a distance processing unit. So that we have another translinear circuit which inverts and normalizes that distance to give us a valid probability distribution. That value is the belief state that the deep machine learning algorithm uses, as well as a winner-take-all circuit to select the most likely element, or the nearest centroid to the input. And then that selected centroid is the one that's updated. We also implement a element of the clustering algorithm that Itmar's group came up with called the Starvation Trace, wherein centroids that have not recently won are given an extra little boost of current to encourage them to be selected and combat the effects of being initialized into empty parts of the input space. So they're pulled in to more dense parts and can actually become useful and fulfill their destiny and be happy. And again, we have the sample and hold so that we can pipeline between the stages. So that's enough transistors for now. But one thing that we do know about transistors, as Itmar pointed out, is that they're not well behaved. They vary in the threshold, conductivity, all sorts of stuff. So we have mismatch, noise, and so forth. And so a big part of this project has been building an error model and determining what aspects of the algorithm were going to be sensitive to mismatch, where we could handle a lot of error. And so what we see here is an error model. It's sort of a reduced error model for simplicity, but that we've inserted these gain errors throughout the block. And so we had a lot of work going back and forth between transistor level simulations in our group and MATLAB level simulations in Itmar's group, where we had to figure out how these algorithms are going to work when you put these crummy transistors into the action. And so what we found, fortunately, was that they're generally pretty robust. And it turns out that noise is generally the big limitation, the big thing that you have a hard time overcoming. And but in general, these algorithms are pretty robust to approximate computation, which was nice to hear. So we built it. And so we're going to start out by looking at a single clustering unit. What you can see here is the red stars. I don't know if is my pointer. Yeah, there we go. So the red stars right here are the initial positions of the centroid. All of these green dots are data that we fed in, and then you can see these tracks show the centroids moving towards the centers of mass of this data. And then the pink ellipses are the variances that we learned. So you can see essentially, it's working. Then we also wanted to test out the starvation trace component of the algorithm. So we initialized it with one centroid set way out in the desert where there was no data to be had. And with the starvation trace disabled, as we expected, nothing happened. That same centroid just remained stuck out there and never won any centroids. And this centroid up here sort of captured 2 of these centroids as a result. When we turn on the starvation trace, it gradually, very slowly initially, but eventually it makes its way over to the data, and everything works. So that's a single clustering circuit. But remember, the deep learning hierarchy system is built of a hierarchy of 7 of those. And it's a little bit harder to visualize that. So what we did is we crafted sort of a simplified character recognition test for this system, where we have this character set, O, X, and plus. And as we present that raw input data to the bottom layer of the hierarchy, let it propagate up, and then use the top level beliefs from the top node as inputs to a very simple classifier. And so doing that, as we increase the percentage of pixels that are corrupted, as you'd expect, the classification accuracy falls off. But when we do that both for our hardware measurements on the bench and MATLAB simulation with no error sources injected, we see that both of those degrade in accuracy essentially identically. So what that tells me is that our error modeling was successful, and the algorithm is in fact robust to the sort of errors that analog computation introduces. We also wanted to see whether there's any beef to the claim that the neuromorphic community generally presents that we have these great savings in power. So we synthesized, we coded up in Verilog a clustering circuit, synthesized that to 130 nanometer digital logic, and ran the simulations, determined the energy per clustering operation, and what we found is that we have about 280 times less energy per clustering task using the analog circuits than the digital circuits. So a pretty dramatic energy savings there. So to conclude, what we've seen is that deep learning systems can provide general purpose spatiotemporal feature extraction, but that they are extremely resource intensive, and analog computation offers a way to access that with reasonable hardware. We've also seen that it can be implemented with no discernible degradation in performance or accuracy relative to a software system or a digital system. And we've also seen that in order to make that happen, there has to be a really tight coupling between the algorithm development and the hardware development. And paying attention to, I really think that one of the things that let this collaboration work is that we're paying close attention to what aspects of the algorithm mapped cleanly to the transistor, the computational primitives that we had available. And so lastly, I'd like to acknowledge our sponsors, DARPA, NSF, and IARPA, and that wraps it up. So.